Hello and welcome to this lecture. From this lecture on, we are going to talk about inner product spaces. So, this notion of an inner product we saw in R2 was very useful to think about angles and direction and give some sort of a geometric picture to R2 very clearly. In R2 also we can see the geometry literally, right? But when you go to larger dimensions in maybe R100 or C100 or something, it's hard to imagine the geometry. But it turns out this notion of inner product gives you precisely that same idea of angles and distances and magnitudes and all that. So, you can roughly draw some sort of geometric figures with vectors once you have a good idea of inner product. It is not exact, but it gives you a lot of intuition. So, let's get started with inner products. Okay. So, we will first define inner products and norms, and that is how we will start. Okay. So, before we define that, let us go back to this motivation of geometry of vectors which we saw in R2. So, just like we did in R2, this notions of length, direction, distance, angle you can visualize for any Fn. Okay. So, here is a little bit of a picture. So, you have the origin which I have shown with one special color here. So, 0 is the origin, 0 vector, and then you may have vectors u, v. These may be in very high dimension, but I can always think of them as like some dots on this plane, so just to visualize, right, to visualize the geometry and draw. And then I could think of sort of the line joining these two vectors in whichever space it is in, and then the line joining u and v in whichever space that is in, line joining 0 and v whichever space that is in, and then think of how far this is, what is this distance, what is this angle, some notions of these angles which respect our usual intuition will be nice to have. So, for this, this length might be thought of as the magnitude of u, this length might be thought of as the magnitude of v, this length might be thought of as the distance between u and v, right. So, in any dimension, how do you think of that? And here is an angle that you think of between u and v, okay. And it can give you very good intuition. So, when you have this kind of a geometric view, you may know how far you are from something, are you very close, too far, things like that are very, very useful in practical applications, okay. So, but how do you define these things? How do you define in a very large space magnitude, direction, angle, distance, and the answer lies in inner products and norms, okay. So, that is what we will do next. The inner product we will define is called the Euclidean inner product in Cn. So, the fact that I am giving it a name means that there are other inner products also. So, one can study inner products more generally. We will not do it in that fashion, we will mostly restrict ourselves, in fact almost completely restrict ourselves to what is called this Euclidean inner product in Cn, okay. So, here is the definition. The Euclidean inner product between u and v, when u is u1 to un and v is v1 to vn, both of these are vectors in Cn, is denoted with this notation. So, these are called angle brackets, okay. So, if you have not seen them before, these are angle brackets. In angle brackets, if I put u comma v, the inner product u v, that denotes the Euclidean inner product in this course. It takes these vectors u v, a pair of vectors, to a scalar. A scalar can be complex in general, okay, a complex scalar, and here is the formula for it. The inner product u v, the Euclidean inner product u v, is u1 times v1 conjugate plus so on, like u2 times v2 conjugate plus so on till all the way till un vn conjugate. So, this bar on top denotes the conjugate, right. So, you remember the conjugate, quick recall, z is a plus ib in complex numbers, z bar or z conjugate is a minus ib. So, I will read this as u1 v1 bar plus so on till un vn bar, okay. So, this is a simple definition for inner product, and like I said, we will prove a lot of results about this inner product which will justify this geometric intuition that I was talking about, okay. So, now I have defined it for Cn. That is because this conjugate is more general, it works like that in the complex numbers, but supposing these are real vectors, then this Euclidean product simply reduces to the standard dot product in Rn, right. So, what is this dot product? U dot v is u1 v1 plus v1 vn, because this conjugate, if a real number, is the same number as itself, it does not do anything when you have a real number. So, this Euclidean inner product. So, we will think of we can think of a real vector as actually being a complex vector also, right. So, in general, we will keep this inner product in mind as far as this course is concerned, but be aware that in the real case it reduces to a dot product, okay. So, here are a bunch of conditions. These are simple conditions, and you will see that these conditions are all satisfied by this Euclidean inner product, okay. So, what is the first one? The first condition is that v comma v, if I take a Euclidean inner product of a vector v with itself, v comma v, it will always be non-negative. First of all, it will be real, okay. So, it will be real, that is not explicitly mentioned here, but the fact that I am saying greater than or equal to and all, it sort of emphasizes that it is real. It is real, it is greater than or equal to 0, and it has equality, it is equal to 0 only when v is 0. So, 0 comma 0 is 0, and any non-zero vector will give you a non-zero value for v comma v. This is a very easy thing to prove. If you do v comma v here, you have v1 times v1 conjugate. What is v1 times v1 conjugate? We have seen that before, right? If you do z times z bar, in fact, you will get a square plus b square, okay. So, z times z bar is a square plus b square. So, in particular, it is real and it is non-negative, right? It is greater than or equal to 0. When will a square plus b square become equal to 0? Only when both a and b are 0 and z is 0, right? So, v comma v is just v1 v1 bar plus so on till vn vn bar. So, it is the absolute value of v1 square plus absolute value of v2 square plus so on till absolute value of vn square, okay. So, this will come back and revisit such products, but this is a very important crucial property for an inner product, okay. So, inner product of any vector with itself is non-negative and equal to 0 only when you have 0, okay. So, that is the positivity property. Then you have a linearity property, and the linearity comes in the first argument of the inner product. If you do AU plus BV and then take a inner product with W, it is the same as taking, U comma W and then multiplying with A, and then V comma W and multiplying with B. You can just plug it in here and check that if you put AU plus BV instead of U here and W instead of W here, it is just a multiplication of this AU plus BV with the W1, W2, and then rearrange the terms and you will get the same thing. It is a very easy thing to prove. I will urge you to try it. So, you can show linearity in the first argument. It is called linearity in the first argument for the inner product, okay. And then finally, it has something called conjugate symmetry. What is this conjugate symmetry? If you take v comma u, if you reverse the order in which you take the inner product, it is not the same as u comma v in general, right, because the one that is getting conjugated changes. If you do v comma u, you will have v1 u1 conjugate. But what is v1 u1 conjugate? That is the same as the whole conjugate of this guy. So, finally, this relationship is true. U comma v is actually v comma u whole conjugate. Finally, you can do a conjugate, okay. So, this is called conjugate symmetry for this inner product. So, this inner product satisfies all these three properties, and we will use these properties quite often when we do simplifications with inner products, okay. So, keep this in mind. In fact, just for those who are interested, an arbitrary inner product is defined in this fashion, okay. It is a mapping that takes two vectors to a scalar and satisfies these three conditions. If you have these three conditions satisfied, then it is called an inner product, okay. So, this Euclidean inner product clearly satisfies these defining conditions, okay. Then further, there are some basic properties for this. It will be very useful in manipulation. You will see what these properties are. First of all, there is a linear map that gets induced by an inner product. If you fix the V, okay, the V is fixed, some fixed vector 1 1 1 1 1 or 1 2 3 4 5, whatever. You fix this vector V, and then think of this inner product UV as a map from U alone to C, okay. So, I guess this C needs to be the complex number C here. I have this small typo. This is this complex number C. So, this if you fix V and then let see this U comma V as a map from the space Cn to C itself, this map is linear, okay. So, this is a useful factor. Remember, there is a linear map that is hidden inside the inner product, linear map from Cn to C, okay, from n to one dimension, okay. That is one thing. Now, what happens with 0? So, this is also a useful thing to remember. If you do 0 comma any non-zero vector, whatever non-zero or 0 or whatever, 0 comma any vector v, it is the same as any vector v comma 0, and both of them become 0, okay. So, once you have 0 here, all the coordinates are 0, you multiply, you will get 0. There is nothing much to talk about here, okay. But notice the notation. This is some notational ambiguity that you have to be careful about. I am using the same notation 0. On the left hand side, it starts for the vector 0, and the right hand side it stands for the scalar 0. We have been doing this a lot throughout this course. I hope that is clear enough to you, okay. And finally, additivity. Now, in the second argument, there is a conjugate being taken. So, it is not quite linear, but additivity is satisfied, okay. So, if you do v comma u comma v plus w is the same as u comma v plus u comma w, you can just plug it in and check. So, if you do v1 plus w1 whole conjugate is V1 conjugate plus W1 conjugate. So, when you multiply by U1, it becomes U1 V1 conjugate plus U1 W1 conjugate. Then you group the terms together, you will get inner product UV and inner product UW. Okay. So, it is a straightforward thing to see. So, this property is also true. Okay. Now, scaling of the second argument introduces a conjugate here. So, this is the only thing in the second argument, it is not purely linear. If you scale the second argument by lambda, instead of u comma v, if you do u comma lambda v, what you end up getting is lambda bar uv, because the second argument is always conjugated, right? You do v1 bar. So, if v1 becomes lambda v1, you will have lambda bar times v1 bar. So, that lambda bar will come out as a constant, but it will not go away. So, it will come not just as lambda, but it will come out as lambda bar. On the other hand, if you scale the first argument, if you do lambda u comma v, it will just be lambda. Okay. So, watch out for that. Scaling in the first argument, we saw that before, is just a linear map. So, it just comes out. The second argument, you will have to conjugate. Okay. So, these are some basic properties, very easy to prove. Just write it down. You will get an answer here in the proof. I am not writing it down in detail, but hope this is clear enough to you. Okay. So, here is an example. So, this is a typical example just to get you used to what kind of manipulations you may have to do with these vectors when you do inner products. Let us say you have u plus 2v and then you are integrating, doing an inner product with u minus iv. Okay. So, notice what I am doing here, it is linear in the first argument. So, it just becomes u comma u minus iv. Second argument I have not touched it, plus 2 times v comma u minus iv. We used linearity in the first argument to write it like this. Now, I attack the second argument. I have additivity in the second argument. So, I can write it as u comma u and then I have u comma minus iv. Now, this minus I is this lambda here. So, it will come out as lambda bar. What is minus I conjugate? It is I. So, it becomes plus I times u comma v, and then 2 times v comma u, and then the same 2 remains, but then v comma minus iv, this minus I will come out as a conjugate. So, it becomes 2i v comma v. Okay. So, you can write it slightly differently, but I do not know if this is accomplishing anything, but this v comma u, if you do not like, you can convert it to u comma v and then put a conjugate there and you get the same expression. So, you see how when you have sums and sums of vectors and you are doing inner product between them, you can simplify it into finally a sum of many different inner products involving the component vectors. Okay. So, this is sort of one example. So, this is just basic definition of an inner product and how to manipulate it and what are the rules it follows. I hope that was clear. Thank you very much.